my channel MuleSoft Unleash. I hope you enjoyed my last video. Today we're stepping into advanced runtime execution and error handling using DataWeave 2.0. Let's begin by understanding this DataWeave 2.0 script step by step, highlighting runtime execution, error handling, and resiliency patterns powered by DW Runtime. We import everything from DW Runtime, which gives us access to powerful runtime capabilities like eval, try, fail, random, wait, and version. Next, we define a simple utility function as a string. This shows that DataWeave can even store executable logic dynamically, which becomes useful when working with runtime evaluation. Now, take a look at the random number function. Here, we intentionally introduce instability. If the random value is greater than 0, 5, the function throws a failure using fail. Otherwise, it simply returns OK. This is a great way to simulate real-world unpredictable failures. Moving to the output section. The first field, onExceptionFail, demonstrates one of the most powerful features of DataWeave, dynamic DWL execution using eval. We execute a DWL script at runtime that intentionally fails, but instead of crashing the transformation, we wrap it inside try. By accessing success, we safely check whether the execution passed or failed. This pattern is extremely useful when you want controlled execution without breaking the entire flow. Next, the user field uses the wait function. This pauses execution for 2 seconds, showing how DataWeave can handle timing and execution control. Then we have library, where we call the random number function inside try. No matter whether the function fails or succeeds, the transformation continues safely. Finally, DWL version returns the DataWeave engine version, which is helpful for debugging and environment validation. Now, let's understand this with a real-world example. After setting up the inputs and outputs like I showed earlier, we define the pricing service function. In real MuleSoft projects, this represents a database lookup, a pricing engine, or a third-party REST API. Here, we intentionally make it unstable. If the random value is greater than 0.6, the function fails. Otherwise, it returns a valid value. This helps us simulate real-world service failures. Partner-specific DWL rules. Now comes the most important part, dynamic transformations. We define a partner rules object that stores a transformation for partner A, a transformation for partner B in production. These rules would usually come from object store, a database, a configuration service. Each rule normalizes partner-specific payloads into a common internal format. Dynamic rule selection. Using the incoming partnerate, we dynamically select the correct rule. This avoids large choice routers, multiple flows per partner. Hard-coded transformation logic. This pattern is heavily used in multi-tenant MuleSoft APIs. Safe runtime execution with eval. We now execute the selected rule using eval, wrapped inside try. This is critical. If the transformation succeeds, we capture the output. Fails, the flow continues safely. Instead of breaking the API, we simply track success or failure. This is a best practice for enterprise-grade integrations. Resilient external service call. Next, we call the pricing service, again wrapped inside try. No matter what happens, the API stays alive. A fallback value is returned. Downstream systems are protected. This is exactly how system APIs should behave in production. Final response construction. Finally, we construct the response we return. Whether the transformation succeeded, the transformed order, or a fallback error object, pricing data with availability status, a delayed user response, and the DataWeave engine version. This gives us business data operational visibility, debug-friendly responses, all in one transformation. We've built a dynamic, runtime-enabled DataWeave script for partner-specific transformations and error handling. Now, let's see how it behaves with different JSON inputs, just like you'd encounter in real MuleSoft projects. Example 1, partner a standard payload. Here, everything is standard. The script selects partner A's rule, transforms the payload, and returns order ID as ORD 1001, total amount as 250, partner as A. The pricing service runs next. If it succeeds, you'll get a pricing value. If it fails, the fallback value 0 is returned. This is the happy path perfect for validating the basic workflow. Example 2, partner B standard payload for partner B. The rule is different, maps order ID and total correctly, ensures normalized output for downstream systems. Pricing service logic and wait delay work exactly the same. This shows that dynamic partner selection works consistently. Example 3, partner A missing order amount. Here we are testing missing fields. The script executes the partner a rule, but amount is missing. If the transformation succeeds, it may return null for total amount. If you had validations in place, it could trigger a safe failure. This demonstrates error-tolerant processing and why runtime try is critical. Example 4, partner B extra fields. The rule only maps order ID and total amount. Extra fields like discount and notes are ignored. This shows how dynamic transformations can filter and normalize data for downstream systems. Example 5, unknown partner C doesn't have a defined rule. The script can safely return an error object. Pricing service and wait still execute. This demonstrates fallback behavior for unknown or new partners, a must-have in multi-tenant APIs. And input validation. Example 7, partner. Are nested order details. Here we test nested structures. The rule currently maps only order ID and total amount. Nested items can be included if we update the rule. Shows how the script can scale for complex payloads. Example 8, partner B randomized amount. This tests edge cases. Total is 0, which might affect pricing calculations. Random failures in the pricing service demonstrate resilient fallback logic, useful for stress testing. And QA scenarios. Key takeaways from testing dynamic rule execution: ensures partner-specific transformations. Try prevents crashes on invalid or incomplete data. Pricing service demonstrates resilient external call handling. Wait and runtime features allow for timing and throttling control. Fallbacks and error objects make your API production ready and defensive. In the next lesson, we'll continue building on this and transform even more complex structures. If you're enjoying the series, make sure you like the video, subscribe, and check the playlist for previous days.